Deu rec, Matheus.
Tá legal. Well, it's a great pleasure to announce our next speaker, Professor Andjel from Université de Provence. Professor Andjel has a remarkable contribution to the area of interacting stochastic systems. And besides that, for us here in Brazil, his role, especially during the years he worked at USP and later at IMPA, have been really fundamental. And we miss him very much. And are very happy with all opportunities to discuss and listen to his always very deep observations. So that's one opportunity more today that we are very happy. And the title of his talk today is One-Dimensional Resource Sharing Systems.
Okay, I'd like to thank the organizers for the invitation. It's always a pleasure for me to be back here. And I also like to thank the very kind and generous words of Maria Eulalia, who was my colleague for the years I was here. And I must say I appreciate her as a colleague very, very much. Okay. So I'm going to talk about resource sharing systems. I'm going to present them as interacting particle systems, as a kind of interacting particle systems. First I'll say is what is it that we usually call an interacting particle system. So that is a Markov process on a space which is most commonly a product space, and sometimes, as in the resource sharing systems we're going to see today, it can be a subspace of this product space. The set S is countable, and it's called the set of sites. In many of the examples of interacting particle system, including the ones we'll see today, this is a finite set. Very often it's a 2-point set, but today it will be a bit bigger than that, but finite. So, since I'm going to talk about one-dimensional resource sharing systems, that means that we are going to consider the case in which S is the integers. So that will be our countable set of what we call the sites. So an element in our state space X, an eta in X, is just a function from Z to the set W. And we will consider that W is of this form, 0, 1, 2, up to some constant, integer constant C, to a power which is a finite set itself, and we're going to call it 1, 2, up to K. The idea in these resource sharing systems is that each site is a server or a person, or maybe a group of persons or a machine that have to perform certain jobs. There may be several types of jobs to be performed by that server. So this K is the number of types of jobs the server will be performing. So you have jobs of type 1, 2, up to K. So when eta of eta being here, you apply to some X and Z. So that gives you a point in W. So you apply to some I there. And this will be the number of jobs of type I that are being performed by the server at X if the configuration of our we are dealing with is eta. Very often, instead of writing eta of xi like this, I'll write eta of x comma I. So this is just the same as what I'm writing up there. So this is, of course, a number in 0, 1, C. And it's the number of jobs of type I being performed at X. Okay, these processes are jump processes. And the jumps are, well, maybe a job of a certain type is arriving at a certain server at a certain time, so at that time, the coordinate eta of xi will increase by 1, or maybe a job is completed. A job of type I is completed, and then eta of xi will decrease by 1. So you have to describe the process, you have to say the rates at which these things happen. So we're going to call lambda I of x eta. This will be the rate at which eta of xi increases by 1 unit. And then we'll have delta I of x eta, which is the rate at which eta of xi decreases by 1. That's when a job is completed. We're going to make the assumption that these rates are translation invariant and that they depend only on finitely many coordinates. By coordinates, I mean the eta of x. Eta of x is the x coordinate of eta. So we suppose the following, that there are functions that do this. Which means that the rate at which a new job arrives at, of type I arrives at x depends on how many jobs of different types you have at the servers which are in the interval from x minus r up to x plus r. And the same for the completion of jobs. We'll assume it is a translation invariant function. It's some other function gi of the same coordinates. Okay, in interacting particle systems, we often use a partial order in our set X. So it is a natural partial order, which so it just saying that eta is greater than xi, these are two configurations, just means that eta of xi is bigger than or equal to xi of xi for all x and all I. The x's being on Z and the i's on the set 1, 2, up to k. Now we're going to introduce some inequalities on the rates lambda and delta. And they are the inequalities that allow us to perform certain things, but they are also quite reasonable in the context of resource sharing systems. We are going to, why do we call, well, first of all, we call this resource sharing systems because we presume that the servers that are not far from each other will share resources. So if a server which is next to X has many jobs being performed, he will need lots of resources. That will somehow reduce the resources of the server X, and which will imply two things. First, that he will be less likely to accept new jobs, and therefore lambda I will be smaller. And then, because he has less resources, his performance is lower, and his jobs are completed in a slower manner, so delta I will also be smaller. So this is expressed like this. Lambda I of x eta is going to be less than lambda I of x xi if eta is bigger than xi. So it's the reverse inequality. And well, for the delta I rates, I'm going to be a little more restrictive on this on here. I'm going to say that this inequality holds if eta is greater than or equal to xi and eta of xi is equal to xi of xi of xi. Well, see, what happens is I want to include the case in which different jobs of type I are being processed somehow independently by the same server, in which case this may be proportional to eta of xi. So I need to put this condition, otherwise I'll be writing something a bit rather contradictory. Okay, so I'm going to give now an example of a resource sharing system, which was the example we first saw, which motivated our work on this. This example is what's called a lost network. So in this lost network, you presume there is a cable, an infinite one-dimensional cable, from which calls are being made, phone calls, say. And you assume that each point has a phone, and you may be calling from one point to another one. But the cable has a finite capacity, which we call C, and we don't allow more than C calls to be present simultaneously in the same part of a cable. So when you consider this example, you have to restrict the state space. It can't be all this. So you do it just like as follows. You write y as being w to the z, where w is 0, 1, 2, c to the k. So here, k is the maximum length of our calls. We can't call a point x to a point y if the distance is bigger than k. And if you do, then you can write x as being the set of acceptable configurations, the one on which not more than c calls are going to any point of the cable. So x is just the eras that are in y that verify certain inequalities, which just say that no more than c calls are being present at the same place. So it's like this. So you see if x minus y is equal to I, the calls that are initiated at y, say y is here, and have a certain length I, will affect what's happening at x if the length is at least x minus y. And this case, the maximum possible length. Then you have to summon all the y's which are to the left of x. And this quantity has to be less than or equal to c to have no more than c calls going through x. And this should, of course, happen for all x. Should happen for all x. So this is our state space in that case. There is a conjecture related to this, this process, this lost network process. But it is in a somehow different context. It's in this different context, instead of having calls going from points in z to points on z, you have calls from points in the real line R, with the same restrictions as here. And Frank Kelly suggests that a certain measure he gives is invariant, and he also says that it should be the unique invariant measure for the process. The conjecture is not fully proved, but Ferrari and Garcia proved it under certain restrictions of the coefficients which I be calling lambda I and delta I. The full conjecture is still not known to hold, although most likely does hold. So here we're going to work in a discrete version of this process, and we did put a maximum length for our calls, which is not present in the Kelly's conjecture, nor in the Ferrari and Garcia work. But we'll say why the process is indeed has a unique invariant measure for all the range of the parameters. Okay. I'm going to say a few words about Markov processes and their construction. if you're able to construct a process that is being described by the rates I gave, and you call eta t the random configuration you have at time t when the initial configuration was eta, then that should give you a certain semigroup of operators, st, applied on functions f. So the functions f are going from x to r, and usually they belong to Cx. They're continuous functions of x. So x was a product space. You assume, put there the product topology, and I mean each w is a finite set. So there you put the discrete topology, and on x you put the product topology, and you consider the continuous functions from x to r. If you are somehow lucky with your process, it is a Feller process, and that means that this is also a continuous function. Well, I haven't defined it, so this is defined like this. You start your configuration this is a new function, and at eta, its value is the expectation of f of eta t, given that you started your process from the configuration eta. So if you have what's called the Feller process, then this is a continuous function too. And st is a semigroup of operators on the continuous functions. Well, for the processes I have described where there is a maximum length for the calls and where interaction has a finite range, these will be Feller processes, so this will be in fact true. Well, for those processes, the usual way they are constructed is not by saying by constructing the process in some manner and then saying defining st this way. It's rather done the opposite way. You sort of construct a semigroup of operators, and once you have a semigroup of operators that satisfy certain conditions, there are big theorems that tell you that from there you have a Markov process eta t, and that the Markov process eta t does satisfy this. But of course, the semigroup has to be related to the rates at which the process evolves, and that's being seen by what's called the generator of the process. If you write st of f of eta, and you subtract f of eta, and you divide this by t, and then you take a limit as t decreases to 0. So this is f at the initial condition. This is the expectation of f at some time t which is small. If you let t go to 0, you have a sort of a derivative here that should tell you what were the possible jumps that would occur in a small time interval. So this will be a certain operator L applied to f and computed at the initial condition eta. Now this operator, this operates on Cx, but it doesn't operate in the whole of Cx. It's a densely defined linear operator. It's defined on a dense domain of Cx, but not on the whole of Cx. It basically looks like this. I won't write it entirely because it's a bit long, but it basically looks like as a sum of some coefficients, which I call of eta and xi, of f of xi minus f of eta. It looks like this, where this is the initial configuration. This is a configuration that you may attain from eta by just one jump, and this is the rate at which that jump occurs. And you sum of all the configurations for which this is positive. So eta and xi differ at only one side, only one of x. So in fact, this is a countable sum because you can't change C simultaneously at several places. Okay, so now that you have your semigroup ST, you say that a probability measure mu on X is invariant for the process. So this is a definition. If this happens. So your probability measure is invariant if this happens. This means, in fact, that if the process was started in a random initial configuration distributed according to mu, then at any later time t, the random configuration you have is also distributed according to mu. There is a way of writing this in terms of the generator of the process, and the equivalent condition for mu being invariant as defined here is to say that LF d mu is 0, where L is the generator of the process, and since you can't apply that to all f's in Cx, well, you have to, it is equivalent to this for f's in a much smaller space than Cx. And it is sufficient if this happens for all f which we call cylinder functions. A cylinder function is a function that depends only on finitely many coordinates. So if you look at f of eta, and f is a cylinder function, it suffices to give you the value of eta of x for x in a finite subset of z to tell what the value of f of eta is. So you just look at those functions, and for those functions you need to have this. If you have this, then your measure mu happens to verify this too. Okay, so one of the big problems in particle systems is what are the invariant measures of a process? And are they unique? Is there one invariant measure, or are there many others? Or are there many invariant measures? Well, you could also ask, is there one invariant measure at all? But in this case, in the process we're looking today, the fact that there is an invariant measure is immediate somehow, because when you are dealing with a Feller process on a compact state space, you always have at least one invariant measure. So the question, rather than existence of invariant measure, is do we have uniqueness? And moreover, there is the question of ergodicity of the process. If you have a unique invariant measure, you want to know whether or not, starting from any initial distribution, you always converge to this invariant measure. So the questions are here: is invariant measure unique? And if so, does the integral of st f of eta, no, it's not that. Does st of f of eta converge to the integral of f of xi d mu of xi for all initial configuration eta, for all eta in x? That would mean that if you start from this configuration and you look at the distribution you have at time t, it converges weakly to the measure mu. If that happens, you say that the interacting particle system is ergodic. So here we want to show that the resource sharing systems in one dimension which have finite range interaction are ergodic. We are not able to show that in all generality. We have a very serious restriction, which is, but in the case of loss networks, this restriction is satisfied, so it is true that the loss networks are ergodic. So what is the restriction? Well, the restriction is that we need to have not just an invariant measure, which we'll always have in these cases, but a reversible measure. So a measure is reversible, loosely speaking, when, as you see the process evolve on time, and you see it going backwards on time, you see the same thing. You see the same thing in distribution. That can be written in terms of equations with a generator too, just as this were the equations for all, you write this for all cylinder function f and you get the necessary and sufficient condition for mu to be invariant. Well, you can write something similar for mu to be reversible. So I'll just say what it is. Mu is reversible if the integral of g L f d mu is equal to the integral of f L g d mu for all f and g cylinder functions. If you have that, then your process is reversible. For the measure mu is reversible. Well, reversible measures are much easier to handle than just invariant measures. And I'll say a bit how this comes into the proof of ergodicity of resource sharing systems having one reversible measure. So let's state the basic result then. So this is a joint work with Lopez and Sanz from the University of Zaragoza. Well, the basic result says the following. If a finite range, one-dimensional, well, RS for resource sharing system, RSS for resource sharing system, has a reversible measure, then it is ergodic. So it has a unique invariant measure, which is a reversible measure, and it does converge to that reversible measure, whatever the initial condition is. So I'll say a few things about the scheme of the proof and how we used things that were known before for what's called the stochastic Ising model. So the stochastic Ising model is another particle system that has a reversible measure. The main difference it has with these is that the rates at which you have jumps are always strictly positive. They're bounded below by some constant. That has some consequences, and I'll say where they come into. So the proof goes like this. It has three parts of different levels of complexity, say. First part is the reversible measure is unique. That is, there is only one reversible measure. Then second part of the proof is to show that every invariant measure is reversible. So once you know that every invariant measure is reversible and the reversible measure is unique, you know that there is just one invariant measure. And the third part is that 2 implies ergodicity, implies that starting from any initial configuration, you converge to this unique reversible measure. So the first part is classic. It's the same as the proof of the stochastic Ising model, basically. There's nothing new there. 2 will come later. 3 is a consequence of a theorem of Mumford. So this is a consequence of Mumford's theorem. So Mumford's theorem implies that once you have a unique invariant measure and you have a one-dimensional interacting particle system, then it is ergodic, if the range of interaction is finite. So this is the case here. We have a one-dimensional interacting particle system. The range of interaction is finite. Once you have a unique invariant measure, Mumford's theorem implies that the system is ergodic. If I have some time later, I'll say a few words about how Mumford proved this. It's most likely to be true in all dimensions. This theorem, my belief is that it's true in all dimensions, but no one knows how to prove it. And even in one dimension, it took a long time until someone did prove it. Okay, so now I'm going to concentrate in this part. Why is it that all invariant measures are reversible? Well, in doing this, we had to use 2 of the most frequently used techniques in interacting particle systems. One is the technique of what's called relative entropy. So the relative entropy technique was first used by Dick Hawley, and it was later used by Hawley and Strook to prove that the stochastic Ising model in 1 and 2 dimensions satisfies this, that every invariant measure is reversible. So we somehow followed the proof of Hawley and Strook, and at a certain stage there is a little difficulty that appears because the coefficients of our process might be 0 for certain values of the configuration, which does not happen for the stochastic Ising model. So there we had to do something else, and there we had to use the other important technique in particle systems, which is coupling. Okay, so how does this work? Well, let's suppose first that you have a finite state Markov chain, or Markov process, say it's in continuous time. And suppose that pi is an invariant measure of this Markov process, of a Markov process, on some state E, which is finite. So E is supposed to be finite here. Then you, if mu is another probability measure on E, then you define the relative entropy of mu with respect to pi. And it's defined like this. Usually you call it h of mu. It's a sum over all x's on E of mu of x times log of mu x over pi x. You adopt the convention that 0 log 0 is 0 here, if need be. Well, why is this useful? Well, because this happens to be monotone on time. If you compute, say mu is initial distribution, you put mu as initial distribution, and you call mu t the distribution of the process at time t, what happens is that h of mu t is monotone. It's decreasing, monotone in t. And it is, if your process is irreducible, it's going to be a strictly decreasing, unless mu is invariant measure pi. Because what you do is this, you compute the derivative, and if mu is invariant, then mu t is equal to mu, so the derivative should be 0. You equal your derivative to 0, and from there you can show that actually mu is equal to pi. So that works very well for finite Markov chains. Here we have processes which are on uncountable state spaces because we have this w to the z. So these are uncountable, and therefore you can't apply this directly. But Holley realized that he could look at the process on a finite box. Instead of looking at the process on the whole of w to the s to the z, you look at on w to some interval, minus n to n, and see what happens there. So so to be able to write a little more the way Holley and then Holley and Stroke proceeded, I'll need to write some more notation. So I'm going to call En the set of x's which are on w to the power minus nn, so the interval minus nn instead of the whole of z, such that c tilde belongs to x. So I should say what c tilde is. I'll say it in words because it's much easier. Xi, you see, Xi is defined, is a configuration defined only for the servers or the interval minus nn. So you need to extend it to the whole of z. Well, you extend it by saying that all the other coordinates have 0 value. So Xi tilde is just extension of Xi by putting all the other coordinates, the ones that are not between minus n and n, as being equal to 0. So you want that to be in the space X. Then you define some sort of relative entropy like this. You write the sum of Xi on En of mu n of Xi, the log, I'll say what mu n is, log mu n of Xi over pi n of Xi, where pi is the reversible measure of the whole process. So assume we have a reversible measure for the whole process on w to the z, or on subspace of w to the z. Mu n and pi n are the projections of the measures mu and pi on this set. So because these measures are defined on really here, but you project them on the coordinates from minus n to n, and you call those projections mu n. And then if by any chance mu is invariant, then this, of course, should not depend on mu t is the distribution you get at time t, if mu is invariant, mu t should be equal to mu. So this should be a constant function in t, and therefore the derivative has to be 0. So that's true. The question is how we're going to use this now. In the stochastic Ising model, this was used by Holle and Strug. And what they did is this. They computed the expression of this derivative, which is a rather complicated expression, so I won't write it down for you. And one of the problems is that since you're looking at the projection of a Markov process on some part of the space, you don't really have a Markov process. So things won't work as smoothly and nicely as they work in the finite set here. You have to do something else. What they were able to do, and for that they used another computation of this expression that was done just before by Moulin, Olagnier, and Pinchon. So they wrote the expression of a derivative here in a very nice manner, and Holle and Strug used that in the following way. So this derivative at t equals 0 is expressed as follows. There is a sum of positive terms, quite complicated sum of positive terms, but as we shall see, quite important, this sum. And then there are some extra terms. So you know that this is equal to 0. If you knew that that the sum of the extra terms is 0, then the sum of the positive terms will be 0 too. And that means that they will all be 0. Well, if they are all 0, it happens that those terms equal to 0 are exactly equations that tell you that the measure mu is reversible. So, so if you knew that this was equal to 0, you were done. You're done. It's finished. But you don't know it. At least you don't know it immediately. Because of the fact that pi is reversible, what happens is that these terms can be written in a very pleasant manner, in a manner which makes them what I will call boundary terms. So here's where the reversibility of pi appears. These are boundary terms, which mean, by boundary terms I mean terms that depend on what happens outside the set minus nn. For what's really happening, these are the boundary conditions when you look at the process from minus n to n. So these boundary conditions have some effect of what happens in the box from minus n to n. And these boundary conditions create these extra terms somehow. So now you would need to know that boundary terms are 0, that the sum of boundary terms are 0. Well, this again, you don't know it directly. But what happens is this. These boundary terms, I'm going to call all this an, because n is just the size of the box, minus n to n, and we'll let n go to infinity later on. And here you have the boundary terms, and let's call this sum bn. So bn, because you are in dimension 1, the boundary of the box is just 2 points, and this bn is a finite sum, really, here. And not only finite, but its size does not depend on n. You see, the boundary of an interval it's always of the same size in dimension 1. So this is a sum like this of some terms where well, maybe I write j. J is on a finite set. Well, then you're going to compute the same with hn plus 1. You do the same computation with hn plus 1. And you're going to have something which is here an plus 1. And the important thing is that you can compare an plus 1 to an and somehow with the terms which are in the boundary of what I call bn. And what happens is that using some convexity arguments, you show that an plus 1 is greater or equal than an plus the sum over j of some constant c times the squares of the b and g's. So let me write this Bn here. This is a sum of B and G's over G on a finite set. And here you're going to find something like this. So you sum the squares, you multiply by C, which is a positive constant, and you get this inequality. So now suppose that you know that Bn is bounded in N. Well, if Bn is bounded in N, then since An is minus Bn, An will also be bounded. So this will be bounded. And because you can write this as An plus the squares of these boundary terms, you would conclude the following, that the sum over N from, say, 1 to infinity of the sum of the B squares and J over J of this finite set, which is the same whatever N is convergent. That you get a convergent sum, because this will be bounded. And at each new step, you add the terms, the boundary terms of N plus 1 and the boundary terms of N plus 2, etc. So you'll get a convergent series. If this is a convergent series, it's because this goes to 0 as N goes to infinity. If this goes to 0 as N goes to infinity, so does this. So Bn is going to 0 as N goes to infinity, which means that An is also going to 0 as N goes to infinity. But An is increasing, so it had to be 0 all the time. And if An is 0, means that you have all the positive terms here which are 0, and that's exactly what you need to conclude that your measure is reversible. Now, so in the case of a stochastic Ising model in dimension 1, this is the way Holly and Stroop proved that every invariant measure is reversible. They proved in dimension 1 and 2. The way I wrote the proof is just in dimension 1. It's somehow more subtle, the proof in dimension 2, but we won't need it because we are working in dimension 1, and for other reasons, we could not possibly do much in dimension 2. I'll talk about that later. But we have a further problem here. Further problem comes from the fact that in the stochastic Ising model, it's easy to see that Bn is bounded. That's a consequence of the fact that the rates are all strictly positive in that process, which is not the case in the processes we are considering. So since the rates are not strictly positive, you need a different proof that Bn is bounded. So I'll say a bit how this proof is done. Take again a Xi and En. So En were the configurations when you look them from minus n to n. You only have the coordinates from minus n to n. And extended again by putting zeros with Xi tilde, as I did before. Then one way to show that the boundary terms are bounded uniformly in n is to show the following. That if you look at the measure mu and you project it on, so remember that also that mu n is a projection of mu on w to the minus nn. So I'm going to write a projection on a bigger set, minus n minus k up to n plus k. And if you're able to show that this is bounded below by some constant which depends on k but is uniform on x's. So it's uniform on n and on x's and en. Then that will be enough to conclude that the boundary terms have a bound which is uniform in n. What does this mean? This means that if your invariant measure gives a certain mass to the configurations which are equal to xi between minus n and n, then it gives a mass which is somehow proportional to it, to the configurations that are equal to xi between minus n and n, and which are equal to 0 on the two intervals to the left and to the right of minus n and n of size k. So here you have minus n minus k, here you have n plus k. So certain configuration here has a certain mass in the mu, and you want the mass of the configurations which are equal to xi here and would take 0 values here. That would be, of course, smaller, but you want it not to be much smaller than this. So you want this quotient to be bounded below by some constant. And this constant can depend on k, but it should not depend on n. If it depends on n, then you'll be in trouble because you wouldn't get a uniform bound on the Bn's. So you need to show this. Okay, I won't have much time to say how this is shown, but I'll say it's shown by means of coupling techniques. So coupling techniques are important in interacting particle systems and in general in probability. Basically, they are like this. You let two processes evolve on the same probability space, and you want them to evolve in a certain way, and certain relations between them are kept. Here, what you need is to show that if you start from some configuration eta, then you can write two versions of the same resource sharing system, the same process, two versions you call eta 1 and eta 2. So you have to couple these versions in such a way that if the first one arrives to the configuration C between minus n and n, then there is a good chance that the second one will arrive to the configuration C tilde between minus n minus k and n plus k. So somehow that condition that this one arrived to C between minus n and n, this one, the conditional probabilities is bounded below, that this one will arrive to the proper C tilde between minus n minus k up to n plus k. This is not the usual way the coupling is done. This is somehow an unusual coupling that is done here. The idea is this: you let the two coordinates here, let's call these the two versions of the process, not rather than coordinates, you let them evolve together as much as possible between minus n and n, and to some extent independently here and here, not entirely independent. If you would let them evolve entirely independent, that wouldn't work. So what you really have to do is to say that you let them evolve independently on certain time intervals, which you have to choose properly, and the choice is non-constructive. In fact, I can't say in which intervals you have to do it, but that there are some intervals that you can choose on time and let them evolve independently of those intervals, and if you do that, your chances of getting the C tilde here when you got C here for eta 1 are good. They're bounded below by this constant CK. Okay, so once you've done that, you got the uniqueness of the invariant measure, and then you applied Mumford's theorem. So I won't have time to tell you how Mumford proved his theorem, but it's also a coupling technique, quite different from the one that was used in this part of the proof. So thanks for your attention.